lecture I will be dealing with a problem on the classical mechanics, on the classical physics, which will be simpler in nature. This is just to give you an intuition about how to apply the laws of Newtonian mechanics onto the physical problems. So in this very problem, consider an example. If we have a particle moving along a parametric curve is given as R equal A times cosine of omega t along the x-axis plus, this is the unit vector along the x-axis, plus b sine of theta, that is sine of omega t, along the y-axis, that is j hat, this is the unit vector along the y-axis. This is the parametric curve, okay? Parametric curve. Parametric means there are different kinds of parameters, that's a, omega, upon which the motion of the particle depends, and these are constants. Actually, parametric curve is given as this R, and a, b, omega, these are all constants of motion, okay, constants. And I and j are the Cartesian unit vectors. You already know them. These are the Cartesian unit vectors along x-axis and y-axis respectively. If there is a k component also, that is the component present along the z-axis also, that means the motion would have been in the 3 dimensions, but here it is only along to the 2 coordinates. That means the motion is 2-dimensional only. So in that case we have to find the force and comment upon the type of force, which type of force is acting onto this very particle if it is moving along the parametric curve this. So motion is given along this very curve. We have to calculate its force and discuss what kind of force it is. So first of all, we will get force by applying second law of motion, but for that we have to calculate acceleration, because acceleration gives, then upon applying the second law of motion we can deduce the force acting onto this body. So for that we have, say for example, this is a cosine and a sine term, so that means the parametric curve will be something like this. It can be any shape which will be which can be seen upon applying this very thing in software, where you can deduce the actual curve. But here we can roughly say that it will be something like this. So consider a particle here. It follows a path like this from time t to t prime, okay? So this will be the path which is traversed by that very particle. So the position vector at any instant of time, R is given by a cosine of omega t I plus b sine of omega t j. This is the position vector of that very point particle along the parametric curve, position vector, okay? So to calculate the acceleration we need to double differentiate this very position vector with respect to time. So differentiating first with respect to time, we will get r dot, that is dr by dt, will be equal to, differentiate this, a is constant, omega is constant, so a kept it is as it is, keeping this as constant. Cosine of omega t, differentiation of cosine of omega t is sine, because differentiation of cos is minus sine omega t, and there is an extra term omega, it will come outside, so differentiation will be minus times omega sine omega t, and differentiation of sine omega t will be equal to plus, because differentiation of sine is plus times cos, that is cosine of omega t with an extra term omega coming out. So we will write it down as cosine of omega t differentiation will be omega sine omega t with a minus sign, okay, along the I-axis, plus b omega cosine of omega t g, because differentiation of sine is cos plus times. Now this will give the velocity along the curve, okay, but we need the acceleration. So for acceleration, differentiating this very equation again, differentiating again with respect to time. So that means d2r by dt squared, that is the r double dot, that is the acceleration, d2r by dt squared. So we have to differentiate this very equation now again with respect to time. So differentiation of sine is cosine of omega t with an extra term omega, and differentiation of cosine of omega t is minus times, here it will be minus times now, minus times sine omega t with an extra term omega, and keeping b is constant, omega constant, a is constant, these will be all constants outside. So we will get minus here, sine omega t differentiation is cos plus cos, so that means we will get minus times a omega cosine of omega t, sine differentiation is cosine omega t with an extra term here omega, already one omega is there, and extra term omega here, it comes out to be omega squared, okay, plus here plus b omega differentiation of, now again with respect to time, differentiating this, cosine of omega t differentiation is minus times sine omega t with an extra term omega, extra term omega gets multiplied to this, it will be omega squared, but minus sine omega t, this will be along I-axis and this will be along J-axis. Fine. So we will get here, we'll get all double dot will be equal to minus here, keep it outside, omega squared here, omega squared here, keep this also outside. What we'll get inside the brackets, it's a here, cosine omega t I along the x-axis, plus, because minus is outside, omega squared is outside, we'll get plus b sine omega t along j-axis. So this will be the acceleration. But if you see onto this, a cosine of omega t, b sine of omega, it is the position vector back. So r double dot will be equal to minus times omega square, this very stuff, and this is r. So we can write it down as acceleration, that is r double dot will be equal to minus times omega square multiplied by this, and this is the position vector itself, that's omega square r, okay. So this will be the acceleration of the body which is moving along some curve with r equal to a cosine of omega t I plus b sine of omega t j. So this, if this is the parametric equation, the particle is moving along this very curve. So for that we have to be cautious that the equation will be given by this, accelerated equation will be given by this, that means the acceleration will be minus times omega square r, and this is the equation of simple harmonic motion. You might have already seen it earlier also, because acceleration is proportional to the position vector r with a minus sign. Minus indicates that it is tending to retreat its path after with the passage of time. Okay, so here in this case it will be like the sinusoidal wave. Fine, so particle will be moving along this very thing, but it will be coming back with certain phase again. Then after it will be retreating its path. In time it will be following the sinusoidal path. Okay, so this very motion is the simple harmonic motion. That means the particle which was under consideration here, moving along this very curve, is actually following the simple harmonic motion, and the acceleration is given by this very equation. Now we are concerned with the force acted onto over this this particle P, which is following this very equation. So for that, to calculate the force, that is the equation A, applying second law, multiplying equation first with mass of the particle, that is m. Say this is the mass of the particle m here. So applying mass of the particle, multiplying throughout, we will get mass times r double dot will be equal to minus times mass times omega square r vector, and r is this, given by this very equation. Okay, so we will get this very equation like this. So mass times r double dot is the force from second law. Okay, using second law of motion, isn't it? So this will be equal to force acting onto this particle which is moving along this very path. So force will be given to as equal to minus times m omega square r. This will be the force applied onto this body. But we have to calculate what kind of nature of the force is, what kind of force is applied onto this very particle. So we have to discuss the nature of force F. So for that we will apply the curl upon this force, evaluating curl. You might have already done this very thing, curl of force. These are all simple problems. So curl upon this, what does curl is represented as delta cross F, and delta means in one dimensional motion, delta is equal to d something by with respect to x, that is the differentiation of that very quantity with respect to x. In two-dimensional it is dx by dt plus dy by d of something by dy, that is differentiating with respect to x and then again differentiating with respect to y. And here in case of this we have to say, for example, we have three-dimensional case, and the curl in three-dimensional is given to be equal to, these are vectors, I along x-axis, j along y-axis, and k along z-axis. What is the I component of this very delta? It is partial by partial x, that is differentiation with respect to x. Along y-axis it is differentiation with respect to y, and along z-axis it is differentiation with respect to z. This is the determinant of this very thing. What is the force component along the x-axis? Okay, we have given this very thing minus m omega times omega square times r, and r is this very thing. Fine. So r has only two components. Along x component is, along this very component is a cosine of omega t, and along y-axis, so here I will be writing f will be equal to minus omega square r. R is equal to omega square r is equal to a cosine of omega t along I-axis plus b sine of omega t along j-axis, that is y-axis. So we have two components. This is constant, say it is some constant a, this is also constant, this is also constant. So we have actually the two factors here. One is cosine component along x-axis and another is sine component along j-axis, that is y-axis, and the third component along the z-axis, that's also missing, that is 0 along k. Fine. So we will be getting some constant, say here it is some star constant times cosine along the I-axis, which is this very thing, cosine omega t, plus some constant along the y-axis, that is sine omega t, and along j-axis, along k-axis, that is the z-axis, it is 0 because it is absent here. So in short, what will be the curl of force? Curl of force, that is, this will be equal to along I, along j, along k. It is partial differentiation with respect to x, partial differentiation with respect to y, partial differentiation with respect to z. Here the component is some constant, say a prime cosine omega t. Along the y-axis it is b prime sine omega t, and along k-axis it is 0. And we know the calculation of determinant, it is done as along this very row, keeping this very row as I hat, then deleting these very two, deleting this and deleting this, then cross multiplying this very thing. So partial differentiation of 0, this will 0, it will vanish, minus partial differentiation of, that is dz by d partial by partial z of b sine omega t, okay, minus j-axis. Now keeping this very thing, deleted this, deleted, then cross multiplying this by this, cross multiplying this by this, so we'll get partial by partial x of this very 0 term, it will vanish, again no meaning of this, minus dz by this very thing, that is partial by partial z of a prime cosine omega t. Similarly with the k term, keeping this very deleted, we will get this multiplied by this, that is partial x of b prime sine omega t, minus this very thing, partial by partial y, that is differentiation of a prime cosine omega t with respect to y. Hope you are getting this. Along the k-axis we will delete this very row and this very row. This is the rule of determinants. So differentiating with respect to x, this will act upon this very quantity b sine omega t, then differentiation with respect to y upon cosine of omega t, which I wrote here. But this is independent of z, as we see that cosine omega t and sine omega t, these are not the functions of x, y and z, because here omega and t are contained. It is a function of time, it is not a function of x nor y nor z. So these are all functions of time, not the functions of the Cartesian coordinate x, y and z. So this will be 0, this will be 0, because differentiation of constant will be 0. This will be 0, this will be 0, and this will also be 0. So that means the whole curl of the force will vanish. Okay, that means the curl will be curl of f will vanish. What does that mean? And this is the mathematical formulation of conservative force. Mathematical form of conservative force, that is if the curl of the force is vanished, that means the force is diverging. It is not curling, okay? It is not rotating. It is not curling around the point particle. Okay, that means the curl is vanished. That means it gets diverged. It is like this is the point particle here. The force comes out like this. This means the force is diverging. If it would have been like this, then there might be some curl present inside a particle. So that means the curl of the force is vanished. That is the mathematical formulation of the conservative force. That means the force is conserved. That means the force which we were discussing along the sinusoidal path, along the curve, which was given by R equal to cosine of omega t and sine of omega t, that very force is actually the conservative force. That means the work done by this force will be independent of the path. That is the outcome of this conservative force of the path it follows. That means the force which we were discussing here, it is conservative in nature. That is the curl of the force vanishes. Okay, this was a simple example. Hope you revise it 2 times if you not get it on the first instance. Okay, so for that you will get this idea about solving the problems like this. I will be dealing with other examples in the due course of time. With that, I'm going to finish it. Please comment in the comment section if you feel any difficulty in understanding this very problem. I will come across those very queries soon. Hope to see you in another video. For now, God bless.